You are about to discover that the moment you were born, the moment someone you have lost last spoke to you, and the moment you will take your last breath are, in the view of our best physics, equally real right now. Not as metaphor, not as consolation. As a consequence of 4 innocent-sounding assumptions Einstein made in 1905, assumptions that your GPS and every atomic clock on Earth now rely on. Tonight, we are going to build the argument slowly, with 2 mirrors, a passing ship, and a supernova. Settle in, turn the lights low, hit subscribe if you like drifting off to strange physics. And stay with me, the floor is about to shift. Part 1. The now you think you are standing in. Right now, wherever you are, something impossible is happening. You are sitting or lying down somewhere, and your body is convinced that this moment is the only one that is real. The chair beneath you is real. The light in the room is real. The faint sound of your own breathing is real. And the moment that came before it, the moment when you opened this video and settled in, that moment is already gone. It went somewhere. You do not know where. It simply left. The moment before that one, whatever you were doing an hour ago, it is also gone. The breakfast you had this morning, gone. The person you used to be 10 years ago, walking around in an apartment you no longer live in, gone. Your childhood, gone. The entire history of the world up to this second, gone. That is the story you have been told by your own nervous system for every single day of your life. Time flows forward. The past recedes. The future has not arrived yet. There is one razor-thin edge of reality called the present moment, and everything outside it is either memory or expectation. That is how it feels. That is what every clock on every wall in every building on this planet seems to confirm. That is what language itself encodes when we say a thing happened, past tense, finished, filed away. I want you, just for the length of this video, to consider the possibility that this entire story is wrong, not slightly wrong, not wrong in the way that everyday intuitions are sometimes sharpened by science, wrong the way the flat Earth was wrong, wrong the way the geocentric universe was wrong, wrong in a way that, once you see it, you cannot put back the way it was before. Every moment of your life, according to the cleanest physical interpretation of the most successful theory in the history of science, still exists. The dinner you ate last Tuesday is not archived, is not remembered, is not preserved as information. It is still there, still on the table, still warm. The afternoon when you were 7 years old, running through a sprinkler in a yard that belonged to someone you barely remember now, is still that afternoon. The last conversation you had with someone you have lost, the last look they gave you, the last time they said your name, is still happening, not symbolically, not in the abstract. In the same physical sense that the room you are sitting in right now exists, those moments exist. They have not been erased, they have not been replaced. They have not gone anywhere at all. We just cannot reach them from where we are standing. I want to be careful here, because this is the kind of sentence that sounds like poetry, or consolation, or metaphysics, and it is not any of those things. It is a consequence of a set of equations that a Swiss patent clerk wrote down in 1905, equations that have since been tested to an accuracy measured in parts per billion, equations that your phone is using right now, underneath everything else it is doing, to figure out where on the surface of Earth you are standing. The satellites in orbit above you are correcting for the fact that their clocks tick at a different rate than yours, and the correction they make is the same piece of physics that tells us the past has not gone anywhere. If Einstein were wrong about this, your navigation app would be unusable. The same argument that puts a blue dot on your map is the argument that tells you your grandmother, whoever she was, still exists somewhere you cannot visit. This view has a name. Physicists call it the block universe. The name was coined, more or less, by a mathematician named Hermann Minkowski in 1908, 3 years after Einstein's original paper, and it has been a live interpretation of relativity for more than a century. Einstein himself embraced it. He spent the last decades of his life writing letters to grieving friends and relatives, in which he referred to the distinction between past, present, and future as a stubbornly persistent illusion. That is his phrase, not mine. I want you to hold on to it, because we are going to return to it several times tonight, and by the end of the video I want you to feel the full weight of what a 76-year-old physicist, weeks away from his own death, meant when he wrote those words to a family mourning the loss of his oldest friend. Here is what I am going to do over the next 2 hours or so. I am going to walk you very slowly through the argument that produces the block universe. We are not going to do the math. You will not need a physics degree. You will need only the 4 assumptions that Einstein made in his original paper, which even a careful listener can follow. And you will need the patience to watch each assumption click into the next one until the conclusion drops out at the end. Every step of the argument is grounded in experimental evidence. Every step has been checked. The argument is not a thought experiment. It is a calculation of what reality must be like if light behaves the way our most sensitive instruments have, for over a century, shown it to behave. Along the way, we are going to slow down at certain moments. I am going to ask you to imagine things. I am going to ask you to stand in a dark room with 2 mirrors and fire photons at both of them. I am going to ask you to watch a woman named Alice glide past you in a spaceship, performing the same experiment in her own frame, and reach a different conclusion than you. I am going to ask you to lift the entire universe out of the present moment and turn it in your hands like a piece of glass and see what it actually looks like when time is not flowing. Some of those passages may stay with you. That is fine. The point is not to remember every number or every experiment. The point is that by the end of tonight, when someone tells you that the past is gone, you will have a very specific, very gentle reason to disagree. A quick word about what this video is not. It is not a promise of time travel. It is not a simulation argument. It is not a claim that you have a secret destiny written into the geometry of the cosmos. The internet has, over the years, extracted a lot of strange claims from the block universe, and we are going to address most of them honestly later on, but none of them follow from the physics in the way the core claim does. The core claim is modest, in a way, and devastating in another. The core claim is simply that the universe has 4 dimensions, and that what we call the passage of time is a property of how our minds slice through those 4 dimensions, not a property of the universe itself. That is it. Everything else is commentary. And yet, once you really see it, that one sentence is enough to rearrange how you think about the people you have loved, the person you used to be, and the moments you are living through right now. I want to thank you, before we go further, for being here. This channel exists because some of you like to fall asleep to the fundamental structure of reality, and I consider that one of the more beautiful quirks of our species. If you are new here, welcome. Get comfortable. There is no urgency to what comes next. If you drift off partway through, that is genuinely fine. The argument will be here when you wake up, and so, incidentally, will the moment you drifted off. That is the point. Nothing we talk about tonight is going anywhere. So, let us begin where the argument begins. Not with equations, with the feeling, right now, that time is moving. Because that feeling, as sincere as it is, as universal as it is, as impossible to shake off as it is, may turn out to be the strangest and most intimate illusion your brain has ever produced. And the reason we can say that, the reason any of us can say that, starts with a man in Zurich in 1905 trying to figure out why a beam of light refuses to speed up or slow down no matter how you chase it. Part 2. The first crack in the river. For most of human history, time was a river. You can find this image in almost every culture that ever wrote anything down. The Greeks called it Chronos, and they pictured it as something that carried human lives along in a current. The Buddhists spoke of impermanence, the constant flowing forward that nothing can resist. In the Western scientific tradition, Isaac Newton gave the river a mathematical form in 1687, when he wrote in his Principia that absolute, true, and mathematical time, of itself, and from its own nature, flows equably without regard to anything external. Newton's time was a universal clock ticking in the background of the cosmos. Every event in the universe happened at a specific moment on that clock, and every observer in the universe, in principle, could agree on which moments happened before which. The past was behind you. The future was ahead. Everyone shared the same now. That picture lasted for almost 2 centuries. It was strong enough to hold up not just classical mechanics, but the entire industrial revolution. Trains running on schedules, factories synchronizing shifts, telegraphs coordinating business across continents, all of them rested on the unspoken assumption that time was one thing everyone could agree on. Newton had given us a universe that ticked, and engineers had built a world on top of that ticking. In the late 1800s, there was no serious physicist who doubted any of it. There were only problems at the edges, little irritations that did not seem to fit. One of those irritations had to do with light. Light, it turned out, behaved very strangely when you tried to pin it down. If you stood still and measured the speed of a beam of light passing you, you got a particular number, about 300 million meters per second, in a vacuum. If you then ran alongside the beam, trying to keep up with it, common sense said you should measure a slower speed because you were already moving in the same direction. A car on the highway going 60 looks stationary from another car going 60. That is how velocities add. That is how rivers work. And yet every time someone set up an experiment to catch light doing what it should have been doing, it refused. In 1887, 2 Americans named Albert Michelson and Edward Morley built an apparatus of astonishing precision in Cleveland, Ohio, designed to detect Earth's motion through what was then called the luminiferous ether, the hypothetical medium that was supposed to carry light waves the way air carries sound waves. The Earth was moving around the Sun at about 30 kilometers per second, and if the ether existed, you should have been able to measure the breeze. Michelson and Morley measured nothing. The ether, if it existed, moved at less than 8 kilometers per second relative to the Earth, which was nowhere near enough to match expectations. The experiment was supposed to confirm something every physicist on the planet believed. It confirmed nothing. It failed beautifully, and the failure haunted physics for 18 years. The 18 years ran out in 1905, when a 26-year-old named Albert Einstein, working at the patent office in Bern, Switzerland, published a paper titled On the Electrodynamics of Moving Bodies. It was one of 4 papers Einstein published that year, any one of which would have earned him a Nobel Prize. And in the context of this video, it is the important one. In that paper, Einstein did not try to explain away the Michelson-Morley result. He simply took it seriously. He assumed as a starting point that the speed of light is the same for every observer, regardless of how they are moving, regardless of how the light source is moving, full stop. And then he watched what followed. What followed, as we will see over the next several parts, was the end of the river. The constancy of the speed of light is incompatible with the idea that all observers share a universal clock. You cannot have both. If light speed is the same for everyone, then space and time themselves have to stretch and squeeze to accommodate different observers. A meter for you is not a meter for a spaceship flying past you. A second for you is not a second for that ship. And, most devastatingly of all, the moment you call now is not the same moment someone else calls now, if they are moving relative to you. The universal clock was a myth. There was no such thing as a single ticking present shared by all of reality. There were only observers, each with their own slice of the universe they called now, and those slices disagreed with each other. Einstein himself, in 1905, did not yet see how radical the consequences would be. That came later, and it came from a man who was not a physicist at all, but a mathematician. His name was Hermann Minkowski, and he had once been Einstein's teacher at the Federal Polytechnic in Zurich. Minkowski had not been impressed with young Einstein as a student. He is reported to have called him a lazy dog. When Einstein's relativity paper appeared, Minkowski read it, sat with it, and then did something that changed physics permanently. He reformulated it geometrically. On September 21st, 1908, Minkowski stood up at the 80th Assembly of German Natural Scientists and Physicians in Cologne and delivered an address that has become one of the most quoted in the history of physics. He said, in words that still feel like a weather system passing through a room, that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. That union is what we now call spacetime. Minkowski took the 3 dimensions of space and combined them with 1 dimension of time, and he treated the combined 4-dimensional object as a single geometric entity. Events, in Minkowski's formulation, are not things that happen in time. Events are points in a 4-dimensional manifold. An object does not move through space over time. An object is a world line, a single continuous curve traced through spacetime from the moment of its creation to the moment of its destruction. Your life, under Minkowski, is not a sequence, it is a shape. Einstein's initial reaction was, you could say, lukewarm. He found the geometric reformulation to be unnecessary mathematical dressing over a physical insight. He is reported to have said, of Minkowski's version, that since the mathematicians had gotten hold of his theory, he did not understand it himself anymore. But Einstein came around, and he came around for a reason. When he tried to generalize special relativity to include gravity, a project that would occupy him for the next decade and produce general relativity in 1915, he could not do it without Minkowski's geometry. The 4-dimensional fabric was not optional. It was the natural home of the physics. Space and time were woven into a single thing, and gravity, as it turned out, was the bending of that thing by the presence of mass and energy. Everything we now know about the universe's largest scale structure, from the orbits of planets to the collisions of black holes that LIGO detected in 2015, rests on Minkowski's 4-dimensional loaf. I want you to notice something about this that is easy to miss if you are not watching for it. The block universe is not a bolt-on to relativity. It is not a philosophical reading of the theory that some physicists adopt and others reject. It is the geometry itself. When you treat time as a dimension on equal footing with space, the natural object that comes out is a 4-dimensional thing in which all events, past and future, have the same kind of reality as events happening now. The notion of a moving present becomes difficult to state in that geometry. It is like asking, on an ordinary map, which point on the map is here? The answer depends on where you are standing. There is nothing in the map itself that privileges one point over another. Minkowski's spacetime works the same way. Events just sit there. Their positions in space and time are relationships, not statuses. There is no point on the map of spacetime that is intrinsically the present. There is only a direction we happen to be facing. Einstein was not a man who used the word illusion lightly. When he came to describe the flow of time that way, he had spent the better part of half a century turning Minkowski's diagram over in his head. Every piece of evidence he saw, every experiment that confirmed special relativity to ever higher precision, every generalization he made to include gravity, quantum mechanics as it emerged, the CMB we would discover in the 1960s, none of it rescued the river. The river dried up. What was left was a shape. The shape has been sitting in our physics textbooks for 116 years, and most people who encounter it for the first time do not notice what it is saying about their own lives. Tonight, I would like you to notice. Because once you see it, you cannot unsee it. And I think the universe is a little more interesting on the other side of that seeing. Before we walk through Einstein's actual argument, which requires 4 assumptions and one very simple thought experiment, I want to leave you with a small question. If time really is a dimension, like the length of a room, then in what sense is the far end of the room less real than the end you are standing at? The far end is over there. You cannot touch it from here. You have to walk to it. But nobody, looking at a room, says that the far wall is not real. It is just in a different place. Space works that way for us without any trouble. And yet, when physics tells us that time works the same way, something in us rebels. Something in us insists that the past must be gone, that the future must not be there yet, that only this breath, this single ticking instant, is real. That insistence is what we are going to dismantle tonight, very slowly, one assumption at a time. It will not hurt, I promise, but it may leave a mark. Part 3. The 4 assumptions that look harmless. I want to lay out Einstein's 4 assumptions now, because the rest of the argument builds on them, and once you see them, you will feel how harmless each one looks in isolation. There is no single moment in the derivation where you can point and say, there, that is the suspicious step. The suspicion is distributed. The conclusion sneaks up on you. The first assumption is that the speed of light in a vacuum is finite. This is not controversial. It is measured. The currently accepted value, and I do mean accepted in the most literal sense, is exactly 299,792,458 meters per second. That number is not rounded. It is not approximate. In 1983, the International Committee that sets the standards for physical units decided to define the meter in terms of the speed of light rather than the other way around. So the speed of light is now, by definition, that exact number. Anytime you see somebody express the speed of light as around 300,000 kilometers per second, they are rounding for convenience. The actual value is fixed forever. It is the backbone of modern measurement. It is the thing against which we now measure all other distances. The second assumption is the strange one. The second assumption says that the speed of light is the same for every observer, regardless of the observer's motion or the source's motion. Read that sentence again. It is easy to skim past, because each individual word is familiar, but what it is claiming is genuinely alien to your intuition. Imagine a highway. 2 cars are going 60 miles an hour. If you are in one of them, the other one looks stationary. Relative velocity. You know it in your bones. Now imagine that the other car, instead of a car, is a beam of light. You and the beam are both traveling at the speed of light. By normal highway logic, the beam should look stationary to you, or at least slower than it looks to a stationary observer on the side of the road. But it does not. If you could somehow accelerate to 99.99% of the speed of light, and you then measured the speed of a beam of light running alongside you, you would measure that beam at 299,792,458 meters per second. The same as always. The same as everyone else measures, no matter how fast they are moving. This is not a quirk of measurement. It is not a trick of the equipment. It is a statement about the structure of reality. Something about the nature of light is unlike the nature of everything else you have ever dealt with. Everything else has a velocity that depends on who is watching. Light has a velocity that does not care who is watching. The Michelson-Morley experiment was the first result that hinted at this, and over the 139 years since, it has been confirmed to a precision you can barely imagine. Modern tests using ring laser interferometers, cavity-stabilized lasers, and orbiting atomic clocks have constrained any possible variation in the speed of light to less than 1 part in 10 to the 17th. Written out, that is a 1 with 17 zeros in the denominator. If there is any direction in space, any frame of reference, any condition under which light travels at a different speed, we have not found it. The universe has told us, at this point unambiguously, that the speed of light is an absolute. The third assumption follows naturally from the second, though it is worth stating separately. Nothing with mass can travel faster than light. Nothing. No signal of any kind, no particle, no wave, no piece of information can outpace a photon in a vacuum. This is not because the technology is not good enough yet. It is because the structure of space-time does not permit it. If you try to accelerate an object with mass toward the speed of light, the object's mass effectively increases, requiring more and more energy to keep accelerating. To reach the speed of light exactly would require infinite energy, which is another way of saying it cannot be done. Every experimental test of this limit, from particle accelerator collisions at CERN, to cosmic ray observations, to gravitational wave detections, is consistent with c as the ceiling. No particle has ever been observed to cross it. This matters for our argument, because it is what makes cause and effect behave the way they do. An event here cannot cause an event there, unless enough time passes for a light signal to travel between them. This creates what physicists call a causal structure in spacetime, a web of constraints that nothing can violate. The fourth assumption is Einstein's principle of relativity, and it is both the oldest and the most important. It says that the laws of physics are the same in every inertial reference frame. An inertial frame is just a frame that is not accelerating, a frame moving at a constant velocity in a straight line. Your living room is approximately an inertial frame. So is an airplane cruising at altitude with the engines steady. So is a spaceship coasting through interstellar space with its thrusters off. In any of these frames, the same physics applies. A ball thrown inside the airplane behaves the same way it behaves in your living room. A chemistry experiment conducted in orbit produces the same results it produces on the ground. The universe does not privilege any particular velocity. It does not care whether you are standing still or moving at 1,000 kilometers per hour. The laws of physics do not change to match you. That fourth assumption sounds almost boring. It sounds like a statement of democratic fairness. Every frame is equally valid. Nobody is in charge. Physics treats everyone the same. And yet, when you combine it with the second assumption, the one about the constancy of light, it is the fourth assumption that breaks the universal clock. Because if the speed of light is the same for you and for the spaceship flying past you, and if the laws of physics are the same for you and for the spaceship, then your clocks have to disagree. There is no way around it. If your clock and their clock both agreed on what time it was, you would have a preferred frame of reference, and the fourth assumption forbids it. The only way to keep the speed of light constant and the laws of physics equal is to let space and time themselves flex. Your meter is not their meter. Your second is not their second. Your now is not their now. You can go back through those four assumptions right now and look for the suspicious one. Which of them would you reject? The first one says light has a finite speed, which is a fact that can be measured in a college physics lab. The second one says the speed of light does not depend on who is watching, which is backed by 139 years of experiments. The third one is a consequence of the second, and everything we have ever thrown at it confirms the speed limit. The fourth one is just a statement that the universe does not play favorites, which is an almost theological assertion of fairness, the one thing physicists are most reluctant to abandon. If you accept any three of these, the fourth makes the most sense of the other three. If you accept all four, the block universe drops out. I have said that over and over, but I want to be precise about what I mean. When I say the block universe drops out, I do not mean it is a philosophical interpretation layered on top of the physics. I mean that if you take these four assumptions and work out their consequences carefully, you get a world in which there is no universal moment called now, in which observers moving at different velocities cannot agree on which events are simultaneous, and in which the only self-consistent way to describe reality is as a four-dimensional object where every event, past and future, exists on equal footing. Minkowski saw this in 1908. Einstein came to see it. The physicists who came after them, Weyl, Gödel, Wheeler, Penrose, Thorne, have not only accepted it, but built their life's work on its back. It is the default view at the level of fundamental physics. The fight over it is philosophical. The physics is settled. I want to pause for a moment because we have covered a lot of ground in a short time, and I want to make sure you are still with me. We have established that time, for most of human history, was treated as a river. We have established that Einstein's four assumptions, in particular the constancy of the speed of light, broke that river. We have established that Minkowski reformulated the broken river as a four-dimensional manifold, and that this geometry is the natural home of both special and general relativity. We have not yet shown, step by step, why any of this forces the conclusion that all moments exist equally. That is what the next part is for. In the next part, I am going to ask you to stand in a dark room with two mirrors, and I am going to ask you to build the concept of now with your own hands. And then, a little after that, I am going to watch someone glide past you and watch your construction fall apart. Before we do that, one last observation. The four assumptions we just laid out are not hypotheses Einstein plucked from the air. Each one has survived more than a century of the most sensitive experiments human beings have ever built. Every time a new generation of physicists has tried to find a violation, they have failed. Every time a new instrument has come online with new precision, it has tightened the constraints rather than loosened them. If the block universe is wrong, it is because one of those four assumptions is wrong, and we have no experimental hint that any of them is. The universe keeps telling us, in voice after voice, that these are the rules. We are now going to find out what the rules imply. And if the implications feel strange, remember that strangeness is not evidence against a theory. Sometimes the universe is simply stranger than the story our ancestors were telling themselves by firelight. Tonight we find out just how much stranger. Part 4, the dark room and the two mirrors. I would like you now to close your eyes, if it is safe to do so, or just settle a little deeper into wherever you are sitting and picture a room. The room is large, larger than any living room, about the size of a small warehouse. It is completely dark, except for a faint ambient glow that lets you see shapes. The air is still, the floor is smooth. You are standing in the exact center of the room. To your left, some distance away, there is a mirror mounted on a stand facing you. To your right, at exactly the same distance, there is a second mirror also facing you. The two mirrors are perfectly equidistant from where you stand. You measured them yourself. You used a tape measure, and then a laser rangefinder, and then a more precise interferometer, and every instrument gave you the same answer. The mirrors are exactly the same distance from you. You are holding a small device in each hand. Each device can fire a single photon, a single particle of light, in a straight line. The photon from your left hand will travel to the left mirror, bounce off it, and return to you. The photon from your right hand will do the same on the right side. You are going to press both triggers at the same time. The photons will fly outward, strike their respective mirrors, and come back. Because the mirrors are equidistant, and because light travels at a constant speed in a vacuum, you expect both photons to return to you at exactly the same instant. You press the triggers, the photons fly, a very short interval passes. The light is too fast to see in flight. And then, perfectly in sync, both photons arrive back at your hands, touching your palms at what your instruments confirm is the same instant. The two triggers registered the returns simultaneously. There is no ambiguity. The round trips were identical. Now, I want to ask you a question. What time, at the mirrors, did the photons bounce? Your intuition says the answer is obvious. The left photon bounced at the midpoint of its round trip. The right photon bounced at the midpoint of its round trip. The round trips were the same length, so the midpoints were at the same instant. The left mirror's bounce and the right mirror's bounce happened simultaneously. Your construction is complete. You have just defined the present moment. Any event that happens simultaneously with the bounces, anywhere in the room, is happening now. You have operational now. You can check your watch against it. You can calibrate every other clock in the building against it. You are not guessing. You are measuring. I want you to hold that construction in your mind, because it matters. You are not abusing the language of physics here. You are using a procedure that any physicist in any frame of reference would accept as a valid operational definition of simultaneity. You define now. You used the constancy of the speed of light to do it. You used the symmetry of your experimental setup. You used logic. There is nothing wrong with the construction in your frame. In fact, Einstein would approve. This is exactly the kind of operational thinking he used in his original paper. You have just done Einstein-style physics. Here is what is about to happen. Another person, call her Alice, is going to glide past you in a ship. The ship is moving at a steady, constant velocity. Let us say along the axis that connects your two mirrors, from left to right as you see it. Alice is not accelerating. She is not turning. She is just coasting smoothly past you, and she has the same equipment you have. Two mirrors, one to her left, one to her right, placed at equal distances from her inside her ship. Two photon guns, one in each hand. And she is about to do exactly the same experiment you just did, using exactly the same procedure, with exactly the same expectation. Here is what Einstein's fourth assumption requires. Alice's frame is just as valid as yours. The laws of physics are the same for her as for you. She is moving at a constant velocity, which means her frame is inertial, which means she is allowed to treat herself as stationary and treat you as the one moving. There is no privileged frame. If you want to say that you are standing still and Alice is moving, that is fine. If Alice wants to say that she is standing still and you are moving past her at the same speed in the opposite direction, that is also fine. Both statements are equally true. Both frames are equally real. This is just the fourth assumption, and if you accept it, some very strange consequences are about to appear. Alice fires her photons. In her frame, she stands at the center of her ship, presses both triggers at the same instant, and watches the photons fly to their respective mirrors. She watches them return to her. She watches them arrive simultaneously at her hands. In her frame, nothing unusual has happened. She has performed the same construction you did, and she has defined her own operational now. The left mirror bounce and the right mirror bounce happened in her frame at the same instant. Simple, clean. She is as certain of her result as you are of yours. Now watch what you see from the outside. You are stationary. Alice's ship is moving past you, let us say from your left to your right, at a velocity we will call v. From your point of view, when Alice fires her photons, the photons do their usual thing. They travel at the speed of light, regardless of how Alice's ship is moving, because of the second assumption. But Alice's mirrors are not stationary. They are moving with the ship. The left mirror in your frame is at the back of the ship, running away from the left moving photon. The right mirror in your frame is at the front of the ship, running toward the right moving photon. One mirror is fleeing its photon, the other mirror is meeting its photon. This changes the geometry. In your frame, the photon chasing the fleeing left mirror has to cover more distance to reach it because the mirror keeps moving away. The photon heading toward the approaching right mirror has less distance to cover because the mirror is coming to meet it. Since both photons travel at the same speed, the photon with less distance arrives first. In your frame, therefore, the right mirror bounce happens before the left mirror bounce. They are not simultaneous. They are separated by an interval of time. In Alice's frame, they are simultaneous. In your frame, they are not. And Einstein's fourth assumption forbids you from saying either of you is wrong. Both frames are inertial. Both frames are valid. Both frames apply the same physics correctly. What has happened is that the very concept of simultaneity, the claim that two events happen at the same instant, has turned out to depend on who is asking. It is not a property of the events themselves. It is a property of the relationship between the events and the observer. Let me say that again, because I think this is the sentence that does the most work in the entire argument. Simultaneity is not a property of events. It is a property of the relationship between events and an observer. There is no such thing, in a world that obeys Einstein's assumptions, as two events simply happening at the same time. There is only two events happening at the same time, according to some observer. Change the observer's velocity, and the simultaneity judgment can change. I want to give you a sense of scale here, because the effect is real, but for everyday velocities, it is tiny. If Alice is walking past you at human speeds, her now is offset from yours by a fraction of a second, so small we do not have a unit for it. If she is flying in a commercial jet, her now is offset by something on the order of a few nanoseconds over the length of her cabin. If she is in a spaceship traveling at 10% of the speed of light, the offset becomes fractions of a second over kilometers of separation, noticeable but not dramatic. If she is traveling at 99% of the speed of light, the offset becomes enormous. Events that are years apart in your frame can be simultaneous in hers, and vice versa. The effect scales with velocity, and at human velocities it is minuscule, which is why we do not notice it, which is why human beings spent thousands of years thinking time was a river. The river looks fine at the speeds we evolved to deal with. The river does not look fine to a muon descending through the atmosphere at nearly Ceph. It does not look fine to a GPS satellite orbiting the Earth at 14,000 kilometers per hour. It does not look fine to a photon traveling between two mirrors in a ship gliding past you in a dark warehouse. It still exists, I told you at the start of this video, about every moment of your life. We have just taken the first real step toward understanding why. Simultaneity is not universal. Your now and Alice's now are not the same. You and Alice, standing in the same room, are not inhabiting the same present. You are two observers, each with your own slice of spacetime that you call now, and the universe has no referee to tell either of you that yours is the correct slice. Whatever sense of a shared present you thought you had with Alice, or with anyone else, is actually a coincidence of low velocities. It is a feature of the world we live in, where nobody moves fast enough for the gap to show up. Start moving fast enough, and the gap shows up. And once the gap shows up, something very strange happens to the idea that the past has gone anywhere at all. That is what we are going to work out in the next part. We are going to take the relativity of simultaneity, the thing we just discovered in this room, and we are going to walk it all the way to the conclusion that every moment of your life and every moment of every life still exists. We are going to use nothing more than the construction you just performed, nothing more than Alice gliding past you in a ship, and nothing more than the innocent-sounding statement that anything simultaneous with you right now is real right now. Those three ingredients are enough. And the result, when we get there, is going to feel like the floor of reality shifting under your feet. Part 5. A supernova at dinner, a supernova at your death. I want you to stay with me through the next 15 minutes or so, because what we are going to do now is take the relativity of simultaneity, which is a real effect we just watched play out between you and Alice, and push it harder. We are going to push it until the conclusion pops out. And the conclusion, when it arrives, is the block universe. The relativity of simultaneity says that two observers moving relative to each other will, in general, disagree about which events are simultaneous. Alice in her ship disagrees with you in the warehouse about when her photons struck her mirrors. That is a mild version of the effect. It is mild because the events are close together in space, the separation between the mirrors is small, and because human velocities are tiny compared to the speed of light. The disagreement between Alice's now and your now in a warehouse at walking speeds is a tiny fraction of a tiny fraction of a second. You will never notice it in everyday life. Your watch will not show it. Your brain will not register it. For all practical purposes, you and Alice share the same present. But the disagreement does not go away when we scale up. It scales up with you. The faster the observers move relative to each other, and the further apart the events are in space, the bigger the disagreement in simultaneity becomes. If Alice is zipping past you at half the speed of light, the disagreement is no longer microscopic. It is measurable. It is seconds or minutes, depending on the distances involved. And if we look at events that are far apart in space, even at modest velocities, the disagreement can stretch into days and years. Here is the example that I think does the most work. Imagine you are sitting at a dinner table tonight. Let us say it is 8 in the evening. You are eating pasta, and across the universe, in a distant galaxy, a massive star is in the process of exploding. Call it a supernova. It is happening, according to some observer, right now, simultaneous with your dinner. Now imagine that there is another observer, a being of some sort, perhaps a hypothetical space traveler, moving through your neighborhood of spacetime at, let us say, 1,000 kilometers per second relative to Earth. That is a fast speed for a space traveler, but it is well within the realm of speeds the laws of physics allow. For that observer, moving in the right direction, the same supernova is not simultaneous with your dinner. It is simultaneous with an event further in your future. Maybe an event tomorrow, maybe an event next week. Maybe, if we pick our numbers carefully and put the galaxy far enough away, an event 50 years from tonight, an event like, say, your death. Think about what we have just said. There exists a frame of reference, moving through your room at a speed we can specify, in which the same explosion of a star in some distant galaxy is happening at the same moment as your dinner tonight in one frame, and at the same moment as your death, 50 years from now, in another frame. Both frames are equally valid. The fourth assumption forbids us from choosing between them. The universe does not pick, and the supernova, whatever it is doing, is just doing it. The event is the event. The moment in your life that the event is simultaneous with depends entirely on who you ask. Now, let me bring in one more piece. There is a philosophical principle, not a physical one, but a natural one, called the reality principle for simultaneity. It goes like this. If an event is simultaneous with me right now, it is real right now. I do not mean that I can see it. I do not mean that I can influence it. I just mean that it has the same status as me. It is a real thing happening in the universe at the same time as I am happening. Your dinner tonight is real right now. The events happening in the room next door right now are real right now. This feels almost too obvious to state. Of course things happening right now are real. What else would they be? But watch what happens when you apply that principle to the supernova example. Your dinner tonight is simultaneous with the supernova in one frame, so the supernova is real right now. The supernova, in another frame, is simultaneous with your death 50 years from now, so your death 50 years from now is real right now in that frame. If both frames are equally valid, and if the reality principle holds in both frames, then your death 50 years from now is as real as your dinner tonight. And then, once you have that, you can apply the same construction to any two events in your life. For any two moments you have ever experienced or will ever experience, there is some distant event and some observer moving at some velocity that allows you to run the same chain. Your first birthday, your 20th birthday, your grandchild's birthday, the last breath you will ever take, all of them stand in the same relationship. All of them are real right now. The only thing that changes from observer to observer is the order in which they say the events happened. The events themselves just exist. This argument has a name. In the philosophy of physics, it is called the Rietvdijk-Putnam argument, after the two philosophers who published it independently in the 1960s, Cornelis Wim Rietvdijk in 1966 and Hilary Putnam in 1967. They did not invent the idea. Minkowski had the geometry in 1908, and Einstein had come to accept it by the 1920s. What Rietveld and Putnam did was lay out the reasoning cleanly enough that philosophers of physics could no longer brush it aside. The argument is airtight, as long as you accept its premises, and its premises are exactly the four assumptions we discussed earlier, plus the reality principle. Reject any one of them, and you can maybe rescue presentism. Accept all of them, and you get a block universe, and you get it as a theorem, not as a metaphor. I know that some of you are probably feeling a kind of low-level protest at this point. Something in you is saying, wait, this is just definitions. This is just word games. The supernova is not really simultaneous with my dinner in any meaningful sense, because I cannot see it, cannot know about it, cannot be affected by it until the light reaches me tens of thousands of years from now. The simultaneity is just a label. The real things are the ones I can causally interact with. That is a reasonable objection, and physicists take it seriously. The technical response is that causal structure and simultaneity are different things. Causal structure is the web of what can influence what, and it is frame independent. Every observer agrees on what can cause what. If event A is in event B's past light cone, meaning a signal travelling at the speed of light or less could have gone from A to B, then everyone agrees A can cause B. Causation is not frame-dependent. Simultaneity is frame-dependent. The relativity of simultaneity only applies to space-like separated events, events that are too far apart for any signal, even a signal at the speed of light, to have travelled between them. Those events cannot cause each other. That is the technical reply. But here is the thing. The reality principle does not require causal interaction. It just requires reality. When you say, your dinner tonight is real right now, you do not mean that your dinner tonight can cause anything in the next instant. You just mean that it exists as a real event in the universe. The claim is ontological, not causal, and the relativity of simultaneity applies to ontological claims as much as to causal ones. You can save presentism by redefining reality as causal reality, meaning that only events I can affect or be affected by are real to me. But that is a dramatic redefinition of the word real, and most philosophers find it unpersuasive. The more natural reading, the one the physics itself suggests, is that reality is not a status that events acquire and lose. Reality is a feature of being somewhere in space-time. Every point in the four-dimensional manifold is real as a point. Your dinner is a point. Your death is a point. A supernova, 50,000 light-years away, is a point. The universe is the set of all such points, and the set does not change with time, because time is one of the axes the set spans. There is an analogy I find useful here, which I have heard attributed to various physicists over the years, so I will not credit it to any one person. Imagine you are looking at a map of a country. The map shows cities, rivers, mountains. New York is on the map. Los Angeles is on the map. Chicago is on the map. Right now, as you look at the map, you are in Chicago. New York and Los Angeles are not in Chicago. They are far away. You cannot walk to them in a step. But nobody, looking at the map, says that New York is not real just because you cannot reach it instantly. New York is a point on the map. It is just a different point than Chicago. Its not being where you are does not make it less real. The block universe says that space-time works the same way. The moment you were born is a point on the map. The moment you died is a point on the map. The moment I am recording this is a point on the map. The moment you are hearing it is a point on the map. None of these points has a special status that says I am the now. They are all just points. They all exist as points. The feeling you have sitting in your chair that there is something special about this point is a feature of your experience, not of the map. I want to be clear about what this argument does and does not claim. It does not claim that you are not moving through time. It does not claim that your experience of change is illusory. Your memories, your anticipations, your sense of one moment leading to the next, all of that is real, as a feature of the structure of your brain and how it processes information. What the argument claims is that this feature of your experience is not a feature of the universe. The universe is the four-dimensional map. Your experience is a pattern inside the map, a pattern that reads the map in a particular order, like a melody being played from a score. The score exists all at once. The melody is how the listener experiences the score. But the musical phrase you just heard did not stop existing when you heard the next one. It is still in the score. That is where it lives. I know this feels like a lot to take in. It is a lot to take in. I took months to internalize it the first time I encountered it, and I still have moments where the old picture reasserts itself, and I catch myself thinking of the past as gone. The intuition is stubborn. That is why Einstein called it a stubbornly persistent illusion. He was not putting down the people who felt it. He was simply naming the phenomenon. We have evolved to be organisms that model the world as a sequence of moments. That is what our brains do. That is what keeps us alive. The universe, at its most fundamental level, does not work that way. It is a four-dimensional structure in which events sit at positions. Our perceptual apparatus draws a line through that structure and calls the line time. But the structure does not have a line, it just has positions. Before we move on, I want to offer one small consolation to the part of you that is still resisting this argument. You do not have to accept the block universe tonight. You can walk away from this video, brush your teeth, go to bed, and tomorrow morning you will still experience time as flowing forward, and nothing I have said tonight will have changed that. The block universe is not a prescription for how to live. It is a description of the structure of the universe, as our most successful physics describes it. You can live a full, meaningful life, believing the past is gone and the future is open. Most people do. What the block universe offers is a different description of what is actually there. Whether to let that description change how you feel is your decision, not physics's. The physics just is. In the next part, I am going to formalize what we have just worked out into the full construction of the four-dimensional loaf. I am going to show you how to take the mirrors and the ship and the supernova and assemble them into a single geometric object that contains every event in the history of the universe. I am going to ask you to imagine that object, because imagining it is the closest any of us can come to feeling what it means. And after that, I am going to ask you to sit with the fact that you are inside it, that you always have been, that every morning you have ever woken up, every person you have ever loved, every decision you have ever made is inside that object somewhere, waiting, though waiting is not quite the right word, because nothing inside the object is waiting for anything. The object simply is. That is what we are building toward, one piece at a time. Is less than break time equals 0, 5s, is greater than. Part 6. The loaf appears. Is less than break time equals 0. 5s is greater than. I want to assemble the loaf now. That is the metaphor I am going to use, and I know it is a slightly strange one, but there is a reason I am using it. When physicists talk about the block universe, they sometimes call it the block. Sometimes they call it the loaf. The loaf metaphor comes from the idea that you can slice through it. You take a knife, you cut it at an angle, and every slice is a three-dimensional snapshot of the universe at a particular moment in time. Different observers slice the loaf at different angles, and each observer calls their slice the present. The loaf is the four-dimensional object. The slices are what we call nows. The slices are not the reality. The loaf is the reality. Here is how the construction goes. We start with you standing in your warehouse. Your mirrors are to your left and right, equidistant. You fire your photons. The photons return to you simultaneously. In your frame, the bounces were simultaneous. Any event in the room, anywhere, that happened at the same instant as those bounces, you call part of your now. You can extend that slice outward. You can include events in the next town over, in the next country over, on the other side of the planet, in the orbit of the moon, on the surface of Mars, at the center of the galaxy, and at the edge of the observable universe, as long as you define them as the events that, in your frame of reference, occurred simultaneously with your mirror bounces. That is your slice of the loaf. That is your now. Alice, gliding past you in her ship, is constructing her own slice. Her mirror bounces happened simultaneously in her frame, so she takes the set of all events in the universe that happened at the same instant as her bounces in her frame. That is her slice of the loaf. That is her now. Because she is moving relative to you, her slice is tilted relative to yours. The tilt is tiny for small velocities, large for velocities near the speed of light. The two slices, yours and hers, intersect only along a thin line, or if the velocities and distances are right, only at a single event. Everywhere else in the universe, your slice and her slice disagree about what is happening now. Now add a third observer, add a fourth, add a fifth. In fact, add every possible observer, each with their own velocity, each making their own slice of the loaf. Every slice is tilted a little differently. Every slice is someone's now. Every slice is populated by events that, to that observer, are simultaneous with their own present. Here is the key move. The reality principle says that events simultaneous with me are real. Apply that principle to every observer. Every observer's slice is populated by real events, which means every event that appears on any observer's slice is real. Which events appear on some observer's slice? The answer is, practically, all of them. Given enough observers at enough velocities, every event in the universe's four-dimensional history is simultaneous with some observers present, which means every event in the universe's history is real. The past is real, the future is real. Events at the other end of the galaxy are real. Events during the age of the dinosaurs are real. Events 1 billion years from now are real. Everything, every when, is real. I want to walk this through your own life, because this is where the argument starts to feel like more than a mathematical curiosity. Take 2 events from your own timeline. Let us pick, for example, the moment you first learned to ride a bicycle and the moment you first drove a car. 2 different ages, 2 different places, 2 different yous. Nothing connects them except that they happen to the same person. In your frame, the bicycle moment is in the past, the car moment is also in the past, and your current moment is separate from both. But now run the construction. There is some observer at some velocity for whom a distant event, let us say a cosmic ray interaction on the surface of a neutron star 10,000 light years from Earth, is simultaneous with your learning to ride a bicycle. There is another observer at a slightly different velocity for whom the same neutron star event is simultaneous with your learning to drive a car. If the neutron star event is real in one frame and real in the other, because both observers are equally valid, then the bicycle moment and the car moment are both real, not as memories, not as information, as events. I am going to step outside the formalism for a moment, because I think it matters. What we have just shown, if the argument is right, is that the little boy or girl who first wobbled on a bicycle outside their childhood home, the one who probably crashed a few times and maybe got helped up by a parent, is still there, still on that bicycle, still wobbling, still a child, not in the sense that you can remember them, not in the sense that their information is preserved in the memory cells of your brain, though that too. In the sense that the event exists as an event in the 4-dimensional structure that is the universe. It has not gone away. It cannot go away. There is nothing in the physics that allows events to disappear. Events are points in a manifold. The manifold does not lose points. It is not a tape that can be erased. It is not a book that can be burned. It is a structure, and the structure contains every event. The same applies to everything else in your life. Your first love, still happening. Your last goodbye to someone you loved, still happening. The moment you laughed so hard you could not breathe, still happening. The moment you cried alone in a room, still happening. Every moment you regret, every moment you treasure, every moment you have forgotten, and every moment you can recall, still happening. Not in some ghostly afterlife, not in a recording, not in a memory, just still there, in the universe, at a position in space-time that you have moved on from, but that you have not erased. You cannot erase it. The universe does not work that way. This is the emotional weight of the block universe. This is where the cold geometry becomes a warm thing, or a terrifying thing, or both at once, depending on how you feel about your own past. Some people find it comforting. They find it comforting to know that the people they have lost are still there, just unreachable. Some people find it terrifying. They find it terrifying to know that the worst moments of their lives are not behind them, but simply at other coordinates of the same manifold they are in now. Einstein, for what it is worth, seems to have found it comforting. So did Minkowski, so did Whale. So do many physicists who live with this picture for long enough. But it is not a package of free comfort. It comes with the full weight of everything you have ever done and everything that has ever happened to you, permanently held in place. Nothing can be undone. Nothing can be redone. Nothing is lost, and nothing is saved from being what it was. It just is. And now, the weight of the central claim starts to settle in. It still exists, every moment of your life. Not as memory, not as information, as the moment itself, at a position in space-time. The dinner you ate last Tuesday is still on the table from the universe's point of view. The person you used to be 10 years ago is still walking around in an apartment you have long since moved out of. Your grandmother, whatever you remember of her, is still doing whatever she was doing at any moment she was alive. From the universe's point of view, you cannot reach any of it. That is the cruelty, if you want to call it that. But you cannot erase it either. That is the consolation, if you want to call it that. The universe is not a tape recorder. It is a four-dimensional object, and every event has a permanent address. I told you at the beginning of the video that I was going to walk you through the argument step by step, and I just did. We have now done the derivation. 4 assumptions, a thought experiment with mirrors, a consideration of moving observers, the relativity of simultaneity, the Rietveld-Putnam argument, and the reality principle. Those are the ingredients. The loaf is the product. It is not a philosophical gloss on relativity. It is what relativity says about the structure of time when you take it seriously. I want to hand you a pause now, because I think you need one, and because the next part is going to be an ambient passage where we simply visualize the loaf together. No arguments, no mathematics, just imagery. In the next part, I am going to ask you to lift the universe out of the present and hold it in your mind. It is going to be slow. You do not have to follow anything. You can drift. You can close your eyes. You can let the words come over you without trying to keep up. That is the intended pacing. Sometimes a concept this strange needs to be held up to the light and turned slowly, the way a jeweler turns a cut stone and looked at from many angles before it settles in. The next part is for turning. Is less than break time equals 0. 5s is greater than. Part 7. The loaf made visible. Is less than break time equals 0. 5s is greater than. I want you to close your eyes, if you can, and stay with me for this part. You are not going to miss anything important if you drift off during this section. In fact, this section is designed to be drifted through. We are going to slow the pace. We are going to visualize. Nothing we say here is going to build on anything earlier. You have already done the hard intellectual work. Now we are going to let the image form. Imagine the universe as a single object. All of it. Every star, every galaxy, every planet, every atom, every person who has ever lived, every person who will ever live. Every moment of every event at every location. All of it woven together into a single four-dimensional shape. Four-dimensional means that in addition to the three dimensions of space you are familiar with, there is a fourth dimension, and that fourth dimension is time. The shape extends in all four directions at once. You cannot see it from inside it, you are part of it, but you can try to imagine it from outside, as a thought experiment. Imagine that you could step outside the universe, which you cannot, but imagine it anyway. You are standing somewhere that is not in the universe. You are looking at the universe from the outside. What do you see? You do not see a three-dimensional scene that is changing over time. You see a four-dimensional object. The object has shape, the object has extent, the object has structure, but the object does not change. It does not evolve. It does not tick forward. It just sits there, complete, from one end to the other. The two ends of the object are what we call, from inside, the beginning and the end of time. One end is the Big Bang, 13.8 billion years ago in our frame. The other end is whatever the ultimate fate of the universe is, which we do not yet fully know, but which physics has some ideas about. In between, the object is filled with everything that ever happens. Galaxies grow and merge. Stars ignite and die. Planets form and orbit and sometimes break apart. And woven into all of it, threaded through the blue planet you happen to be on, are the world lines of every living thing. Every ant that ever crawled across a leaf. Every bird that ever caught a thermal and soared. Every human being who ever drew a breath. Every person you have ever loved. Every face you have ever memorized. Every voice you have ever held in your ears. Each of those lives is a thread. The thread begins at a point in the four-dimensional object, the point we call birth. The thread ends at another point, the point we call death. Between those points, the thread traces out a continuous curve, a world line, a path through space-time. The thread is not thin. It has a shape, because a body is a shape, but it is thin enough, relative to the scale of the universe, to look like a thread. Zoom in, and you can see the details, the person's daily activities, their movements through the world, every meal, every conversation. Zoom out, and it is just a filament. Now, imagine your own thread. It begins at the point in space-time where you were conceived, a specific moment on a specific planet in a specific galaxy. It extends outward through the days of your life you have already experienced, through the moments you are experiencing right now, and on into whatever future you are going to have, ending at the point where your body finally stops being a body. Your entire life, from beginning to end, is a single filament in the four-dimensional loaf. The filament is finished, in the sense that all its points exist, whether you have experienced them yet or not. Now, imagine the threads of everyone you know. They are there too, woven in alongside yours. Your parents are threads. Your grandparents are threads, extending back into regions of the loaf that you never experienced firsthand. Your friends are threads, some of whose paths will run beside yours for decades, some only for moments. If you have children, they are threads whose beginnings are somewhere near you. If you have lost someone, their thread is still there, extending back to wherever they began and forward to wherever they ended, a complete shape in the loaf, not erased by their absence from your now. You can expand this picture as far as you like. Every human being on Earth right now is a thread, most of which extends back decades into the loaf and some unknown distance forward. Every human being who has ever lived is a thread that begins somewhere behind the Big Bang end and ends at some point in the interior, a closed curve that does not come back out. All of those threads together make up humanity's share of the loaf, a single intricate tapestry woven into the blue planet's region. Now zoom further out. The planet itself is a world line, tracing a helix as it orbits the Sunday. The Sun is a world line, orbiting the center of the galaxy. The galaxy is a world line, falling toward other galaxies under gravity. Every object in the universe is a world line, and every world line is embedded in the loaf, and the loaf is the whole thing, all of it, every object, every event, every moment. Nothing is moving. Let me say that again. Nothing in this picture is moving. Because motion is change over time, and in the loaf, time is a direction, not a process. The loaf does not evolve. It simply is. What you experience as motion from inside is the fact that your thread extends in a particular direction through the loaf, and your consciousness slides along the thread like a bead on a wire. But the wire does not move. The bead does not really move either, in any frame that captures the whole loaf at once. It just has a position, and the position is parameterized by how far along the wire you are, and we call that parameter time. I want to let this picture sit for a moment. It is a strange image. It takes time to get used to, and even then, most people cannot hold it in their minds for more than a few seconds before their intuitive picture of time snaps back into place. That is fine. You do not need to hold the image continuously. You just need to know it is there. You need to know that the universe is more than the thin slice you happen to be experiencing. The slice is real, but it is not the whole. The whole is the loaf, and the loaf contains everything. Some people, when they first encounter this image, feel claustrophobic. They feel that if every moment is fixed, then they are not free. Their lives are predetermined. They are puppets being dragged along pre-drawn threads. I understand the instinct, but I think it is a misreading. The block universe does not say your life was written by anyone or anything. It says only that your life, as a shape, exists. Whether that shape was determined in advance by physics, whether it was shaped by your decisions, whether it is the product of randomness or necessity or something in between, the block universe does not specify. All of those interpretations are compatible with the geometry. The geometry just says the shape is there. Other people, when they first encounter this image, feel peaceful. They feel that nothing has been lost. Their grandparents are still somewhere. The afternoon they remember from childhood is still an afternoon. The moments they have cherished, the moments they still miss, have not been erased. They are simply at different addresses in the same structure the person is in now. That is the feeling Einstein seems to have carried with him, judging by his own letters. Whichever of those feelings is closer to yours, or whether both feelings are there at once, or whether the picture simply leaves you confused and a little tired, those are all fine responses. The universe is under no obligation to feel one way to us. It is only obligated to be what it is. The physics says what it is. The feelings are ours. When you are ready to move on, we are going to return to the argumentative mode. In the next part, we are going to look at the experiments that have confirmed, in ways you can measure with your phone, that this picture of time is not a hypothesis. It is how the universe actually behaves. We are going to look at muons falling out of the sky. We are going to look at atomic clocks flown around the world in the 1970s. We are going to look at the GPS network, without which your navigation would not work. Every one of those is a direct confirmation that time does not flow the way your intuition tells you it flows. And if time does not flow that way, then the past is not what your intuition tells you it is. It is still there. It is still existing. It just is not reachable from where you are standing. Is less than break time equals 0, 5s. Is greater than part 8. Muons from the sky and clocks in airplanes. Is less than break time equals 0. 5s is greater than. You might be tempted, after the last few parts, to think of the block universe as a beautiful thought experiment, a philosophical curiosity, a clever mathematical structure that happens to fall out of Einstein's equations, but that does not really describe the universe you live in. I want to spend this part dismantling that temptation, because the block universe is not a thought experiment. It is the physical reality that your technology is built on. Every device in your pocket assumes it. Every experiment we have run in the last century has confirmed it. If the block universe were wrong, the world would not work the way it works. Let us start with muons. A muon is a subatomic particle, very similar to an electron but about 200 times heavier. Muons are unstable. In their own rest frame, a muon lives for about 2.2 microseconds before it decays into lighter particles. That is 2.2 millionths of a second, not long. Muons are produced, among other places, in the upper atmosphere of Earth, when cosmic rays from interstellar space slam into atoms in the air and knock off showers of secondary particles. These showers include muons, which are created at altitudes of around 15 kilometers above the ground. 15 kilometers is about 9 miles. Here is the puzzle. A muon, moving at the speed of light, which is the maximum possible speed, would cover only about 660 meters in its proper lifetime of 2.2 microseconds. That is less than a kilometer. So a muon produced 15 kilometers up, even moving at the absolute maximum speed the universe allows, should decay long before it reaches the ground. By naive calculation, almost none of those upper atmosphere muons should ever hit Earth's surface. There should not be any muons in your backyard, and yet there are. If you set up a detector at sea level, you will find a constant shower of muons passing through it. Roughly 1 muon per square centimeter per minute hits the surface of the Earth at any given moment. You are being struck by muons right now. They are passing through your body as we speak. They are raining down from the upper atmosphere, and they are arriving in far greater numbers than any naive calculation would predict. How is this possible? The answer is that the muons experience time dilation. From the muon's own point of view, only a couple of microseconds pass between its birth and its decay. But in our frame of reference, the frame of the observer standing on the ground, the muon's internal clock is running slow, because the muon is moving relative to us at nearly the speed of light. The slower the internal clock ticks, from our perspective, the longer the muon lives, from our perspective. By the time the muon has travelled the 15 kilometers down to us, its internal clock has ticked only a little, even though, on our clocks, many microseconds have passed. Time dilation stretches the muon's lifespan in our frame long enough for it to make it to the ground. Alternatively, from the muon's point of view, the distance to the ground is not 15 kilometers. Length contraction squeezes the distance so that, in the muon's frame, the trip to the surface is only a few hundred meters. The muon does not have to live long because it does not have far to go. Both descriptions give the same answer. Both are correct. Both are consequences of Einstein's assumptions. And both can be measured every day in every cosmic ray detector on Earth. The muon rate at sea level is a direct confirmation that time dilation is real, that length contraction is real, and that the geometry of space-time is what Einstein and Minkowski said it was. If time flowed uniformly, the way our intuition insists, there would be no muons at your desk right now. The fact that there are is the universe telling you, at every moment, that your intuition is wrong. Let me give you another example. In October of 1971, two physicists named Joseph Hafele and Richard Keating took 4 cesium atomic clocks, extremely precise clocks that lose or gain less than a nanosecond per day under normal conditions, and put them on commercial jet flights. 2 clocks went eastward around the world. 2 clocks went westward around the world. When the flights returned to the United States Naval Observatory, they compared the clocks that had flown with the clocks that had stayed on the ground. Special Relativity predicted that the moving clocks would run at different rates than the stationary clocks, and that the rate difference would depend on their velocity relative to the center of the Earth. General Relativity predicted an additional effect because the flying clocks were higher up in Earth's gravitational field, and gravity also slows clocks. Combining the two effects, the calculation predicted that the eastward flying clocks would lose about 59 nanoseconds relative to the ground, and the westward flying clocks would gain about 273 nanoseconds relative to the ground. The measured results were 59 nanoseconds lost within 10 nanoseconds of error, and 273 nanoseconds gained within 7 nanoseconds of error. Both predictions confirmed. The clocks did not agree on how much time had passed. They disagreed because they had different velocities and different altitudes, exactly as relativity said they would. The universal clock did not exist. The clocks told different stories, and the stories were exactly what Einstein said they would be. Hafele and Keating's experiment was a direct test of special and general relativity in a laboratory the size of an aeroplane, using the civilian aviation system of the early 1970s. It worked. The predictions matched the measurements. That experiment is now 55 years old, and every refinement of it since, with better clocks and better control of the variables, has confirmed the same picture. Clocks running at different velocities, at different altitudes, disagree about time in exactly the way the block universe geometry requires. Now consider the GPS network. Every GPS satellite carries an onboard atomic clock. The satellites orbit the Earth at about 20,000 kilometers of altitude and move at about 14,000 kilometers per hour. At that altitude, gravity is weaker than on the surface of the Earth, so the satellite clocks run faster than ground clocks by about 45 microseconds per day due to gravitational time dilation. At that speed, the satellite's motion relative to the ground causes their clocks to run slower by about 7 microseconds per day due to velocity time dilation. The net effect is that the satellite clocks run about 38 microseconds per day faster than clocks on the ground. Every day, every satellite. If we did not correct for this, GPS would not work. The timing difference between satellite and ground would accumulate. And since GPS determines your position by timing how long radio signals take to reach you from multiple satellites, a timing error of 38 microseconds per day corresponds to a positional error of about 10 kilometers per day. Within hours of launch, GPS would be useless. Within days, it would be placing you in the wrong country. Every GPS satellite is programmed with a clock correction that accounts for both the special and general relativistic effects. Without that correction, the system fails. With the correction, the system tells you where you are to within a few meters. Every time you use your navigation app, you are relying on the fact that time does not flow uniformly across the universe. You are relying on the relativity of simultaneity, the dilation of moving clocks, and the warping of time by gravity. You are using, every day, the same physics that tells us the past has not gone anywhere. I want to give you one more example because I think it drives the point home. In 1938, a physicist named Herbert Ives and an engineer named George Stilwell performed an experiment at Bell Labs using fast-moving hydrogen ions. They shot a beam of hydrogen ions through a vacuum tube, looking at the light the ions emitted as they glowed. Moving light sources produce a Doppler shift, the same effect that makes an ambulance siren sound higher in pitch as it approaches and lower as it recedes. Classical physics predicted one value for that Doppler shift. Special relativity predicted a slightly different value because of time dilation acting on the emitting ions. The difference was small but measurable. Ives and Stilwell measured the shift. It matched Einstein's prediction, not classical physics. That experiment has been refined many times since, using lasers, atomic beams, ion storage rings, modern optics. In every refinement, Einstein's prediction has held up. The current precision is at the level of 1 part in 10 to the 8th, 100 million times more accurate than the original measurement. Every refinement confirms the same thing. Time dilation is a real feature of the universe. The laws of physics take different forms for observers moving at different velocities, because space and time themselves are different for those observers. There is no universal time. There are only local times, each particular to its frame, all woven together into the four-dimensional loaf. I could keep going. I could tell you about the Pound-Rebka experiment in 1959, which measured gravitational time dilation on a tower at Harvard. I could tell you about the NIST ion trap experiments from 2010, which measured time dilation effects at walking speeds and at altitude differences of 33 centimeters, the height of a small ladder. I could tell you about the more recent cold atom clock comparisons at the level of 1 second of drift in 30 billion years, which have put constraints on possible violations of Lorentz invariance so tight that any deviation from Einstein's picture, if it exists, must be buried in the deepest corners of physics we cannot yet access. The cumulative weight of all these experiments is overwhelming. The block universe is not a philosophy. It is not an interpretation. It is the geometry required by the physics of light, and the physics of light has been tested to absurd precision in every laboratory we can build. If the block universe is wrong, you would not be listening to this video, because the satellites carrying this video's data to you would not know where they were. The universe keeps proving, measurement by measurement, that time does not flow, it sits. The loaf is solid, and your dinner last Tuesday is still on the table from the universe's point of view, because the universe does not know how to take it off. That should be enough to establish, I think, that the picture is not a flight of philosophical fancy. The picture is what your phone runs on. Every time you get directions, you are using the same physics that tells you the past is real. Every time you check the time on an atomic clock, you are using the same physics that denies a universal now. The block universe is not elsewhere. It is here, in the room with you, quietly making your technology work. If you want to argue with the picture, you will have to argue with your GPS. Good luck. In the next part, I want to turn to the hardest question the block universe faces. If the past exists, does the future also exist? Does tomorrow already have an address in the loaf, or is the loaf still being assembled at its leading edge, like a building under construction? That turns out to be a much harder question than the question about the past, and there is no agreed answer. But the debate itself is interesting, because it reveals how physicists try to reconcile relativity with quantum mechanics, with thermodynamics, and with the strange experience of being a creature that perceives time flowing forward. Let us go there next. Is less than break time equals 0? 5s is greater than. Part 9. Is tomorrow already written? Is less than break time equals 0? 5s is greater than. We have spent the first half of this video building the argument that the past has not gone anywhere. Now we face a harder question. If the past is real, is the future real too? Is tomorrow sitting in the loaf, at its own coordinates, waiting for you to arrive? Or is the loaf still being assembled at its leading edge, like a roll of film being exposed one frame at a time? This is where the physics gets less settled, and where the debate becomes genuinely difficult. I am going to walk you through the positions, because understanding the disagreement will, I think, help you see what the block universe is really claiming and what it is not. The strict form of the block universe, the one we have been discussing, is called eternalism. Eternalism says that all events, past, present, and future, have the same ontological status. They are all points in the four-dimensional manifold. None is more real than any other. Your birth, your death, the Big Bang, and the heat death of the universe in the far future all exist equally. This is the position Einstein seems to have held, the position Minkowski's geometry most naturally suggests, and the position most contemporary philosophers of physics take when they read the equations of relativity straight off the page. The main challenge to eternalism comes from a position called the growing block universe, which was proposed in 1923 by the British philosopher Charlie Dunbar Broad, and has been defended in recent decades by the physicist George Ellis and others. The growing block universe agrees with eternalism about the past. Past events exist. The block is real to the extent that it contains what has already happened, but the growing block disagrees about the future. The future, on this view, does not exist yet. The loaf is being extended, slice by slice, at its leading edge, and the leading edge is where reality is being added in real time. Think of it like a crystal growing in solution. The crystal is real, but it is still acquiring new atoms at its boundary. At any given moment, there is a definite crystal and a definite boundary, and the boundary is advancing. The growing block has an intuitive appeal. It preserves the idea that the past is fixed, which is what most of us already believe, while also preserving the idea that the future is open, which is what most of us also believe. It says that nothing of what has already happened can be changed or erased, but that what has not yet happened is still genuinely undetermined. The future is not written, it is being written. The problem with the growing block is that it has trouble surviving the relativity of simultaneity. We already saw that two observers moving relative to each other disagree about which events are simultaneous. If the growing block has a definite leading edge, a definite present, then whose present is it? Yours or Alice's on her ship? They disagree about which events are happening now. If you say the leading edge is your present, then Alice's present is partly in your past and partly in your future, and that is hard to reconcile with the idea that the past is fixed and the future is open. You and Alice would disagree about which regions of spacetime are real and which are not. That is a strange thing for reality to do. Usually, reality is not a matter of opinion. Defenders of the growing block have tried to get around this in a few ways. One approach is to argue that there is, after all, a preferred frame of reference in the universe, the frame defined by the average motion of matter, and that this frame provides the leading edge. The cosmic microwave background, the afterglow of the Big Bang, does in fact define a frame of reference in which the universe looks most symmetric. Our solar system is moving through this frame at about 370 kilometers per second, in a direction roughly toward the constellation Leo. This is a real, measured fact, and the CMB dipole has been mapped to high precision by satellites like COBE, WMAP, and Planck. That last one, the Planck satellite, gave us the measurement as 369.82 kilometers per second, with an uncertainty of about plus or minus 0.11 kilometers per second. Very precise. So the CMB provides, in some sense, a cosmic reference frame, but the CMB rest frame is not a preferred frame in the relativistic sense. The laws of physics are still the same for every observer, whether moving with the CMB or against it. The CMB just happens to pick out a frame in which the universe looks most uniform. Using that frame as the leading edge of the growing block is an ad hoc move. The physics does not require it. Most relativists reject this approach because it reintroduces, in a sideways manner, the preferred frame that special relativity forbids. Another approach is to tie the leading edge to quantum mechanics. Quantum mechanics has its own temporal asymmetry. In the most standard interpretations, a quantum system is described by a wave function that evolves deterministically in time, according to the Schrödinger equation, until a measurement is made. At the moment of measurement, the wave function collapses to a definite state, and the collapse is not deterministic. It is random, weighted by the probabilities encoded in the wave function. This collapse happens now, in some sense, and it introduces genuine indeterminism into the universe. Some physicists, including George Ellis and Lee Smolin, have argued that the collapse defines the leading edge of the growing block. Before a quantum event is measured, there are multiple possible outcomes, and none of them is real yet. After the measurement, one outcome is real, and that outcome has been added to the loaf. The universe is growing as measurements occur. This approach is more promising than the CMB approach, but it has its own difficulties. The first difficulty is that quantum measurement is itself poorly understood. The measurement problem, the question of what counts as a measurement and when collapse happens, has been a live debate in physics for almost a century. Different interpretations of quantum mechanics give different answers, and some of them, like the many worlds interpretation, deny that collapse happens at all. The second difficulty is that quantum correlations, especially those established by entanglement experiments, do not respect the relativity of simultaneity either. If a measurement on one particle instantaneously affects its entangled partner light years away, and if both observers doing the measurements can be in different inertial frames, then the notion of which measurement came first is frame dependent. You cannot have a consistent leading edge that works for all observers. The third difficulty is the arrow of time, which is not where many people expect it. You might think that because physics has a past and a future, and because we experience the flow of time going from past to future, there must be something in the fundamental laws of physics that picks out a direction. But there is not. The microscopic laws of physics, as far as we know them, are either time symmetric or very nearly so. If you take any process that physics allows and reverse it in time, the reversed process is also allowed by physics. Two billiard balls colliding can be run forward or backward, and both versions obey the same laws. A particle decaying can be run backward, and the reverse process, particles combining, is also allowed by the symmetric laws, even if it is extraordinarily improbable. The laws of physics have a near-exact symmetry called CPT, which stands for charge parity time. If you flip the charge of every particle, flip left and right, and run time backwards, you get a system that obeys the same laws as the original. CPT symmetry is a theorem in quantum field theory, not just an empirical observation. It is baked into the mathematical structure of the laws, which means that, at the level of fundamental physics, there is no preferred direction of time. The microscopic laws do not know which way is forward. Where does the arrow of time come from then? The current best answer, which is not universally accepted but is the leading candidate, is that the arrow of time is a feature of the initial conditions of the universe, not the laws. The universe started out in an extraordinarily low entropy state at the Big Bang. Entropy, roughly speaking, is a measure of disorder, or, more precisely, a measure of how many microscopic configurations correspond to a given macroscopic state. The Big Bang universe was as ordered as a universe can be, which sounds counterintuitive because the Big Bang was hot and dense, but the relevant order is gravitational. All the matter was nearly uniformly distributed, and in the presence of gravity, uniform distribution is a special state. From that special starting point, the universe has been increasing in entropy ever since. Stars have formed, gathered matter unevenly, burned out, exploded, and the distribution of matter and energy has become more disordered over time. The second law of thermodynamics, which says entropy tends to increase, is a statistical consequence of the fact that the universe started in a low entropy state and has been relaxing. The arrow of time is not a fundamental feature. It is a statistical feature of the particular initial conditions we happen to start with. If the universe had started in a high entropy state and were relaxing into a low entropy state, our arrow of time would point in the opposite direction. The underlying laws would not know the difference. What does this mean for the block universe? It means that even if we experience time as flowing forward, the flow is not built into the structure of the universe. The structure is the four-dimensional loaf, static, timeless, from its own outside perspective. Inside the loaf, entropy has a gradient. Entropy is lower at one end than the other. We call the low entropy end the past, and the high entropy end the future. That is what time's arrow is. It is a gradient in the distribution of disorder across the loaf. The loaf itself does not tick. The universe does not tick. So here is where the debate stands. on whether the future exists. If you hold strictly to the geometry of special and general relativity and ignore quantum mechanics, the future exists exactly as much as the past does. They are both just regions of the loaf. If you incorporate quantum indeterminism seriously, you can make a case that the future does not exist yet, that the universe is being extended by measurement events, but you pay a price in the form of preferred frames or other difficulties. Most physicists who have thought about this carefully end up, I think, somewhere between full eternalism and the growing block, often with a shrug about exactly where the line falls. The past, at least, seems to be locked in. That is the claim that survives all the variations, and that is enough for the core emotional weight of the block universe to stand. Your grandmother still exists. The dinner you ate last Tuesday still exists. Whether tomorrow also exists is the kind of question that gets physicists into heated conversations, but your past is not going anywhere. The universe does not tick. We have said this before, but it is worth saying again, because the sentence does a lot of work. It is easy to read quickly and miss. The universe does not tick. The laws of physics do not single out a preferred present. The geometry of spacetime does not contain a moving spotlight of now sweeping from past to future. Whatever ticking you feel, whatever sense of one moment becoming the next, is happening inside you, not inside the universe. The universe is the loaf. The loaf is silent. The ticking is yours. Is less than break time equals 0, 5, s is greater than. Part 10. The trapdoor beneath the trapdoor. Is less than break time equals 0, 5s is greater than. Just when you have gotten comfortable with the idea that the universe is a four-dimensional loaf, modern physics opens a trapdoor beneath the loaf. There are reasons to think that even the four-dimensional structure we have been discussing is not fundamental. There are reasons to think that space-time itself, as an object, might be emergent from something deeper, and that the something deeper might not have time in it at all. This is the cutting edge of theoretical physics, and it is speculative, but it is serious speculation pursued by some of the most rigorous minds in the field. I want to take you through it, briefly, because it adds one more layer to the strangeness of what the past is and what existence even means at the bottom. The first hint that spacetime might not be fundamental comes from the attempt to combine general relativity with quantum mechanics. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes the behavior of matter in terms of wave functions and probabilities. The two theories have been fantastically successful on their own. When you try to put them together, they break. The equations give infinities. The predictions become nonsense at very small scales. Somewhere below a certain length, called the Planck length, at about 10 to the minus 35 meters, the classical picture of spacetime as a smooth continuum fails. What replaces it? Nobody fully knows. The leading candidate frameworks for a theory of quantum gravity, such as string theory, loop quantum gravity, and others, all suggest, in their own ways, that space-time, at the most fundamental level, is made of something else. String theory suggests that the basic objects are one-dimensional strings whose vibrations give rise to particles, and that space-time emerges from their interactions. Loop quantum gravity suggests that space itself is granular, quantized at the Planck scale, and that time is not a continuous parameter, but a series of discrete steps. There is no consensus on which framework is correct, but they share the intuition that space-time is not the bottom of the hierarchy. Something lower is doing the work. One of the more remarkable results in recent decades is a conjecture called the ADS-CFT correspondence, proposed by Juan Maldacena in 1997. Maldacena showed, in a specific class of toy universes called anti-de Sitter spaces, that a gravitational theory defined on the interior of the space is mathematically equivalent to a non-gravitational quantum field theory defined only on the boundary of the space. That is, a three-dimensional theory with gravity is exactly dual to a two-dimensional theory without gravity. The two theories describe the same physics, but one has an extra dimension, the other does not. This is surprising enough to be called the holographic principle. The idea is that information about a volume of space can be encoded entirely on the boundary of that volume, like a hologram, a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. If the holographic principle is true of our universe, and many physicists think it might be, then the three spatial dimensions we perceive are themselves emergent from a two-dimensional layer of quantum information. Time, the fourth dimension, might be similarly emergent from something without time in it at all. A more recent extension of this idea is the ER equals EPR conjecture proposed by Maldacena and Leonard Susskind in 2013. The conjecture says that quantum entanglement, the mysterious correlation between particles that so troubled Einstein, is the same thing as a microscopic wormhole connecting them. Einstein, Rosen, and Nathan Rosen studied wormholes in the 1930s, and the Einstein-Podolsky-Rosen paper in 1935 introduced the paradox of entanglement. Maldacena and Susskind suggested that these two papers were describing the same phenomenon from different angles. If that is right, then the fabric of space-time itself is woven from the pattern of entanglement between quantum systems. Space is not primary. Entanglement is primary. Space is how the entanglement looks to creatures like us. If entanglement is the fundamental thing, and if entanglement does not itself carry a preferred direction of time, then the four-dimensional structure we live in might be a projection from a more basic quantum structure that is genuinely timeless. At the most fundamental level, there may not be a loaf at all. There may be a network of quantum correlations, and space-time, with its loaf and its arrow and its past and its future, may be what that network looks like when you coarse-grain it into a classical description. This takes us to one of the strangest results in the history of theoretical physics, the Wheeler-DeWitt equation. In 1967, John Wheeler and Bryce DeWitt were trying to write down the fundamental equation of quantum gravity. They applied the standard procedures of quantum mechanics to the gravitational field itself, and they got an equation that had a peculiar property. The equation had no time variable in it. It was a constraint on the possible states of the universe, with no parameter describing how those states change over time. The universe, according to the Wheeler-DeWitt equation, does not evolve. It just is. Whatever time we perceive is supposed to emerge from the relationships between different parts of the universe, not from any fundamental time parameter. This result was so strange that physicists spent decades trying to figure out what it meant. Some concluded that time is an illusion at the most fundamental level, that only relationships between subsystems are real, and that the flow of time we experience is a particular way of reading correlations in a timeless whole. Julian Barber, a British physicist, has argued this position most forcefully in his book The End of Time, published in 1999. Barber imagines the universe as a large collection of static configurations, which he calls Platonia, after Plato's realm of eternal forms. Each configuration is a possible three-dimensional snapshot of the universe. There are infinitely many of them, and they all exist as mathematical objects. Time, in Barber's view, is just the way certain configurations appear to sit in certain orderings, because we happen to correlate information between them. There is no ticking. There is no flow. There are only configurations, and the memories we have of previous configurations are embedded in the configurations themselves, creating the illusion of succession. If Barber is right, or if anything like him is right, the block universe is not even the bottom of the picture. The block universe is already a classical approximation. The real thing is a timeless structure of configurations, or perhaps a network of quantum entanglements, or perhaps some deeper pattern we have not yet learned to describe. But at whatever level we drop to, time as a flowing process does not appear. It only appears when creatures like us read the structure in a particular way. I mention these frontier ideas not to convince you of them, because they are speculative and contested, but to show you how far the rabbit hole goes. If you start from the simple observation that the speed of light is constant for every observer, and you follow the argument carefully, you get the block universe. If you then ask what the block universe itself might be made of, you get holographic, entanglement-based, or configuration-based descriptions in which time is even less fundamental than it looked from the block universe level. At every step further down you go, the universe becomes more static, and the flow of time becomes more of a feature of perception than a feature of reality. We are staring, here, into the trapdoor, beneath the trapdoor. The past, according to relativity, still exists. The past, according to quantum gravity, may not have been the kind of thing that could have not existed, because the geometry that would have contained it was never the ground floor. Ask a theoretical physicist what existence even means at the Planck scale, and you will get a long pause and then a careful answer about how the word loses its ordinary meaning. The physics there is not yet written, but everything we do understand points in the same direction. The universe is not what our ancestors thought it was. It is not a three-dimensional scene that changes over time. It is a four-dimensional structure, which may itself be a projection from a deeper, timeless thing. Your experience of the flow of time, as real as it feels, is the sound of a particular kind of creature slicing through all of that in a particular way. Is less than break time equals 0, 5s. Is greater than Part 11. The claims that do not follow, and the one that does. Is less than break time equals 0. 5s is greater than. The block universe has a shadow on the internet. It has attracted a collection of viral claims that do not actually follow from the physics, and I want to address them one by one, because I think the channel's job is to walk through what the physics says honestly, including what it does not say. If we accept the picture I have just walked you through, 4 assumptions: relativity of simultaneity, the loaf, the experimental confirmations, the deeper speculations, we still have to be careful about what follows and what does not. The first viral claim is that the block universe proves free will is an illusion. The argument goes like this: if every moment of your life already exists in the 4-dimensional loaf, then your future choices are already written. Whatever you decide to do tomorrow, the decision is already there, at its coordinates in space-time, waiting. You are not choosing, you are just discovering what has always been written. Therefore, free will is dead. This argument sounds compelling, but it commits an error. It conflates the existence of your future choices with their being predetermined by forces outside you. The block universe says only that your future choices exist as events in the loaf. It does not say what causes them. On any reasonable interpretation of agency, your future choices are caused, in part, by your reasoning, your values, your preferences, your circumstances. The decisions you will make are the products of your own thinking, which is itself a process happening inside the loaf. The fact that the decisions exist as events at their coordinates does not mean they were made for you. It means they will be made by you, and that they, once made, will stay made. Whatever your philosophy of free will, the block universe is compatible with most of them. Compatibilists, who believe that free will is a matter of the causal structure of decision-making rather than a matter of open futures, generally think the block universe preserves free will. Libertarians about free will, who believe that choices must be genuinely open at the moment of decision, do have a harder time with the block universe, but even they can adopt a growing block to preserve their position. The point is that the block universe does not, by itself, settle the free will debate. It leaves it open, the way relativity leaves a lot of things open. The second viral claim is that the block universe proves time travel is possible. The argument goes, if the past still exists, it should be reachable. Just find a way to get back to it. Some physics forums take this to mean that with enough energy or the right kind of space-time bending, we could visit our own pasts. This also does not follow. The past existing and the past being reachable are two different things. General relativity does allow, in principle, for closed time-like curves, world lines that loop back on themselves and return to their own past. Kurt Gödel found such a solution in 1949 in the form of a rotating universe model. The Kerr solution for a rotating black hole admits them under certain conditions. The Tipler cylinder, a theoretical rotating cylinder of infinite length, would allow them. Traversable wormholes, if they could be constructed, would allow them. But every one of these solutions requires exotic matter or unphysical conditions, negative energy densities, infinite cylinders, matter distributions we have never seen in nature. Stephen Hawking proposed in 1992 what he called the chronology protection conjecture, which argues that quantum effects will always prevent the formation of closed time-like curves when they are about to form. The conjecture is not proven, but most physicists suspect something like it is true. Time travel, in the sense of visiting your own past, is not forbidden in principle, but it appears to be arbitrarily far from practical. The block universe, therefore, does not promise time travel. It promises persistence. Those are different. The past is there. It is just not reachable from here. The third viral claim is that the block universe proves we are in a simulation. The reasoning is that a four-dimensional static structure is exactly what a computer simulation would look like. Every frame pre-computed, the sensation of time emerging from the observer being stepped through the data. A static universe matches the output of a game rendered ahead of time rather than frame by frame. Therefore, we are running in something. This claim confuses the form of the universe with evidence about its origins. A static four-dimensional universe is the natural output of relativity without any simulator. You do not need a simulation hypothesis to get a block. The block comes from the constancy of the speed of light and the relativity of simultaneity and the geometry of space-time. A simulated universe would look like this too, but that does not mean our universe is simulated. The simulation argument, which Nick Bostrom formalized in 2003, rests on different premises involving the relative computational power of future civilizations and the frequency of simulations they would run. The block universe neither supports nor undermines the simulation argument. They are independent questions. Do not let anyone tell you that one implies the other. The fourth popular reading of the block universe is different. It is not a viral conspiracy claim, but a philosophical consolation. Some physicists and some lay readers find in the block universe a response to the experience of grief. If every moment of a lost loved one's life still exists, then the lost loved one is not really gone. They are at other coordinates of the loaf. Death becomes a change of address rather than a disappearance. This reading is sincere, and it has a distinguished lineage. Max Tegmark, the physicist, has written about it. Julian Barber, who takes a more radical, timeless view, has written about it. Einstein himself, as we will see in the next part, wrote about it in his own private correspondence. I want to be clear that physics does not, by itself, tell us how to grieve. Physics tells us how the universe is structured. What consolation or terror we derive from that structure is up to us. But I do not think the consolation reading is a misunderstanding of the physics. It is a legitimate response to what the physics says. If the past is real in the same sense that the present is, then it is not straightforward to say that someone who lived fully and whose life is now a complete shape in the loaf has been erased. The person's thread is still in the structure. That is what the physics says. What you make of that is your own. What does follow from the block universe and what does not is worth stating plainly. What does follow is that the past has not gone anywhere. The past is real. Every moment of your life, every person you have ever met, every event that has ever occurred, still exists at its coordinates in the four-dimensional manifold, according to the cleanest reading of our best theory of space and time. What does not necessarily follow is anything about free will, time travel, simulation, or how to grieve. Those are downstream questions, and the answers depend on additional premises the block universe does not supply. What follows, above all, is a reframing of existence. The universe is not a process that happens to us. The universe is a structure we are embedded in. The past is not a backward-looking telescope. The past is a region of the structure we have already passed through. The future is either a region we will pass through or a region that is still being laid down, depending on which interpretation you favor. But either way, the word exist loses some of its usual temporal weight. Exist is not a status that events have temporarily. Exist is a description of being somewhere in the manifold. Your dinner last Tuesday has that description. Your grandmother, at every moment of her life, has that description. So does the moment you are listening to right now. So does, probably, the moment you will wake up tomorrow. None of those moments is more real than any other. They all just are. In the last part of this video, I want to return to a person. I have spoken mostly about concepts so far, but Einstein, the physicist who gave us this picture, was a person, and he lived his life in the universe he described. He lost friends. He watched people he loved get old. He got old himself, and near the end of his life, in a letter he wrote a few weeks before his own death, he tried to articulate what the block universe meant to him in the face of loss. That letter is, I think, one of the most remarkable documents in the history of physics. It is also a good place to close. Let us go there. Is less than break time equals 0. 5s is greater than, part 12, a letter in March. Is less than break time equals 0, 5s. Is greater than, it is March of 1955. The month is almost over. In Princeton, New Jersey, a man is sitting at a wooden desk in a modest house on Mercer Street. He is 76 years old. His hair is white and unruly in the way that has become famous. He wears a wool cardigan. He has been ill for some time with an aortic aneurysm, and he knows, though he does not yet speak of it publicly, that he does not have long. He has refused surgery. He has told his doctors that he wants to go when it is time to go, and that artificially prolonging life has no appeal for him. He is, in other words, at peace. Within 3 weeks, he will be dead. 3 days earlier, on March 15th, his oldest friend in the world has died in Switzerland. Michel Besso, a Swiss-Italian engineer, has died at the age of 81. Besso had been Einstein's friend for more than 50 years. They had met as students in Zurich, worked together at the Swiss Patent Office in Bern, and talked physics constantly through the years in which Einstein was developing special relativity. Besso is the only person Einstein acknowledges by name in the original 1905 paper on the electrodynamics of moving bodies, the paper that gave us the 4 assumptions we have been working with all night. In the final paragraph of that paper, Einstein thanks Besso for steadfast help, acknowledging that conversations with Besso were essential to the formulation of the theory. Without Besso, there might not have been a special relativity in 1905. There might not be a block universe in your mind right now. And now, Besso is dead. Einstein writes a condolence letter to Besso's family, to his sister and his son. The letter is short. Einstein is not a man given to excess in correspondence. But in the middle of the letter, he writes a sentence that has, over the decades since, become one of the most quoted sentences in the history of science. He writes, "And I am going to translate from the German that Michel has departed from this strange world a little before him. He writes that this means nothing, and then he writes, for those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion." I want to sit with that sentence for a moment. It is not a boast. It is not a theoretical statement being dropped into a condolence letter for effect. It is, I think, a man in his last weeks, writing to a grieving family, using the clearest physical picture he has of the structure of reality to offer them what comfort he can. He is saying, in effect, your father, your brother, is not gone. He is just at other coordinates of the loaf. The distinction between past, present, and future, the distinction that makes death feel like a disappearance, is an illusion that our minds produce. In the universe that physics describes, your loved one is still alive, somewhere in the four-dimensional structure. At every moment, he was alive. The physics does not erase him. Physics does not know how. Einstein knew, of course, that this was consolation. He was not claiming that Besso's friends and family could reach him, visit him, hear his voice again. He was not promising that they would be reunited with him in some afterlife. He was offering something stranger and, I think, more honest. He was offering the claim that the universe, as physics describes it, does not remove the people who die. Their lives remain real in the precise sense that every physicist since Minkowski had been articulating. Besso's thread is still in the loaf, every moment of it. Every conversation he ever had with Einstein, every time they walked together, every laugh they shared, every difficult discussion about relativity in the cafes of Bern is still at its coordinates, still happening, still existing in the way that events exist in a four-dimensional universe. Einstein died 3.5 weeks later, on April 18th, 1955, at Princeton Hospital. He had just finished a page of calculations. His last words were in German, which the attending nurse did not understand. According to his wishes, there was no public funeral. His body was cremated. His ashes were scattered at a private gathering in the Delaware River. He is not buried anywhere. He has no grave. If you were to look for him on the surface of the earth, there would be no place to go. And yet, according to the physics he himself gave us, he is not gone. His thread is still in the loaf. Every moment of his life, from the Ulm of his birth in March of 1879 to the Princeton Hospital of his death in April of 1955, is still at its coordinates. The boy playing with a compass and marvelling at the invisible force that always pointed north, still marvelling. The young man at the Swiss patent office, writing by candlelight, still writing. The famous old man at the desk on Mercer Street, offering consolation to his friend's family in a shaky hand, still writing, all of it, still there, according to the physics, not as a metaphor, not as memory, as events, permanently in the structure, unerasable by anything the structure can do to itself. I want to come back to you, now, sitting wherever you are sitting, with the lights low or the headphones on, a little while away from wherever your life happens to be touching the four-dimensional loaf right now. I told you at the very start that the past has not gone anywhere. I told you that every moment of your life still exists. I hope, after going through the argument piece by piece, that the sentence does not feel like a mystical claim anymore. It is a consequence of the geometry of relativity, which has been tested to extraordinary precision, which your phone relies on every day, which every experiment we have ever run is consistent with. The past is real. The moments you have lived have not been erased. The people you have lost are, in the geometrical sense, still alive at every coordinate of their lives. I also want to come back to the open question, the one we cannot close tonight, the one that has been sitting in the middle of the room this whole time. Why does it feel, from inside, like time is moving? Why does it feel like we are sliding forward through the loaf, moment by moment? Why does the present feel so vivid, so immediate, so undeniably now, when the physics says there is no now at all, only a slicing we happen to perform? The answer to that, as I said earlier, is not known. It lives somewhere in the overlap between physics, consciousness, and the measurement problem of quantum mechanics. Carlo Rovelli, in his book The Order of Time, suggests that the flow of time is an artifact of how our memories form. Memories accumulate in one direction because that is the direction in which entropy increases inside our brains, and we interpret the gradient of memory as the flow of time. David Albert has argued that the past hypothesis, the assumption of low initial entropy, is the fundamental source of our temporal intuition. Julian Barber, as we have seen, argues that time is a convenient fiction generated by the relationships between configurations. None of these views is proven, none of them has experimental confirmation, but all of them share a common thread. The ticking you feel is not ticking in the universe, it is ticking in you. You are the strangest thing in the loaf. You are the part of the four-dimensional structure that thinks it is moving. You are the part that grieves what has not been erased and hopes for what may already be written. You are the part that watches a video about the structure of time and feels, in real time, that the words are arriving one after another, even though, from the universe's point of view, the whole video is a single object sitting in spacetime with all its parts simultaneously in place. You are the part of the loaf that asks why the loaf feels the way it feels. I do not have an answer for you. Physics does not have an answer for you. What physics has is a description of the shape. The shape is the loaf. Inside the loaf, entropy flows, consciousness flows, experience flows, but the loaf itself is silent. The universe does not tick. And yet here you are, feeling that it does. Maybe, if you stay with the image long enough, it starts to feel less like a claustrophobic cage and more like a kindness. Everything you have ever lived, every person you have ever loved, every evening spent with someone you will never see again is still there. At coordinates you cannot reach from your current position, but that exist just as much as your current position does. Einstein, near the end of his life, found comfort in that. So did Minkowski. So do many of the physicists who work with this picture every day. It does not bring anyone back. It does not make loss hurt less in the moment. But it does, maybe, place what we have lost on the same ontological footing as what we have. That is a small thing. It is also, I think, not nothing. Before I let you go, whether you have followed every step of the argument tonight or drifted somewhere in the middle and come back at the end, I want to thank you for coming on this walk with me. This channel is a place where we try to sit with the implications of physics honestly, in a voice that is calm, and let the strangeness settle at its own pace. The universe is strange. You do not need me to tell you that. But occasionally it is strange in ways that are specifically tender, and I think the block universe is one of those ways. The past has not gone anywhere. Your moments are not being erased as they happen. The universe is not a tape recorder losing its data. It is a four-dimensional structure, and the structure holds. If you are still here, consider this a gentle invitation. Subscribe if you would like to walk through more of these late-night questions with me. Like the video if it helped, or if it did not help but was at least interesting. Settle in. Stay until the end of whatever this is, or drift off and come back. Nothing about any of that is in a hurry. The universe, as far as we can tell, is not in a hurry either. A final thought before we close. Einstein's letter to Besso's family ended with a line I have not yet given you in full. He wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." He was 80 years of friendship away from the boy he had been when he met Besso in Zurich. He was 21 days away from his own death, and he signed the letter. And then, presumably, he looked up from his desk, and the spring light came through the window, and the world, as it always does, kept going, or seemed to, from the inside. Outside, in the only view that matters to the physics, nothing went anywhere. Everything stayed. It still exists. Every moment of your life, every moment of his, every moment of theirs. Every moment of whoever you have loved, and whoever has loved you, and whoever you have not yet met, but will meet, and whoever you will love in the years to come. It is all in the loaf. The loaf is the universe. The universe does not tick. Sleep